What is the total pressure exerted by a gaseous mixture that consists of 8.00 grams of methane and same amount of ethane in a 3.50 liter container maintained at a temperature of 35.2 degrees Celsius? Okay, so we've got a mixture of two gases, methane and ethane. The problem, unfortunately, did not give you the chemical formula for methane, and you do need that. CH4 is the chemical formula. And since the problem is asking for the total pressure, we have to use Dalton's law of partial pressures, which says that the total pressure in a particular system is going to be equal to the sum of the pressures or partial pressures of all the gases in that particular mixture. So it could have any number of gases. In this problem there are two gases, so specifically the total pressure in this problem is going to be equal to the partial pressure of methane, CH4, plus the partial pressure of ethane, which is C2H6. So our job here is first to calculate the partial pressure of these two gases individually based on the amount present, 8 grams for each of them, the volume of the container, and the temperature. So that means we're going to have to use the ideal gas law, as in the previous problem, to calculate the pressure of each of the two gases. So let's spell that out here. Our ideal gas law equation is PV equals nRT, and we're solving for pressure, so let's make it very specific. The pressure for the methane gas is going to be equal then to the number of moles of methane times the gas constant times the temperature divided by the volume, and all of this is going to be applied for methane. And the partial pressure of ethane is going to be a similar equation. We're going to have the number of moles of ethane times the gas constant R times the temperature over the volume. So here everything that applies to ethane. Now the nice thing is the only thing that's going to change between these two gases is going to be the number of moles. R, the gas constant, of course, is going to be clearly constant, the same for both of these two gases. The temperature must be the same. We're in the same container, so the temperature is going to be the same for both, so that is not going to change. And the same thing with the volume. The volume is fixed. We're told 3.50 liters, so that's going to be the same for the two gases as well. So the only thing that changes is the number of moles. So the other thing we have to flag before we get started, our temperature must be in kelvins. We're told that the temperature is 35.20. So let's take our 35.20, we're going to add to that 273.15, and we're going to end up with 308.35 kelvins as our temperature, and of course that's going to be used in both of these calculations. So we now have, well, almost everything. We need to calculate the number of moles, so let's do that. Let's first calculate the number of moles of methane. So N sub CH4 is going to be equal to our 8.00 grams of methane times the molar mass. 1 mole of methane has a molar mass of 16.04 grams. So our grams of methane cancel. And when we do the division here, we get a value of 0.499 moles of methane. Now we're going to do a similar calculation for ethane. N sub C2H6 is going to equal also 8.00 grams. That's the mass we were told in the problem that we had. Times 1 mole of ethane has a molar mass of 30.07 grams. So our grams of ethane cancel. We're left with moles. We do the math on that, we get a value of 0.266 moles of ethane. Okay, so now we can calculate the pressure of each of these two gases. And let me just rewrite the equation. Our pressure is going to be equal to nRT over V. So our pressure for methane, CH4, is going to be equal to the number of moles of methane. Let's highlight that in yellow. Number of moles of methane is 0.499. So that's going to be in the numerator. 0.499 moles. Our gas constant will be given to you 0.0821 liter atmospheres per Kelvin mole. And our last term upstairs is temperature. We calculated it in Kelvin. Let's highlight that in blue. 308.35. 308.35 kelvins. And then downstairs is the volume of this container. In the problem, we're told that the volume was 3.5 liters. So let's put that downstairs. 3.50 liters. Liters cancel. Our moles cancel. And our kelvins cancel. We're left with atmospheres upstairs, which is good. There's nothing else. We're looking for atmospheres because we're calculating a pressure. So now we do the calculation. Our pressure for methane is 3.61 atmospheres. Let's circle that in red because we need that number. We're going to have to calculate now the pressure of ethane and then add the two pressures together. So we want to make sure we keep that number sacred. So the second calculation, C2H6, pressure for ethane. Number of moles is the only thing different. Let's highlight in yellow. Our pressure, number of moles for ethane, 0.266 moles. .266 moles. Gas constant's the same, 0.0821 liter atmospheres per Kelvin mole. And our temperature is the same, 308.35 kelvins. Downstairs the volume is the same, 3.50 liters. All the units must cancel the same. Liters are gone. Moles are gone. Kelvins are gone. Again, we're left with atmospheres. We're calculating a pressure. So our unit is consistent with what we want. We turn on our calculator, we get a value of 1.92 atmospheres as the pressure of ethane. So now we're going to simply add these two numbers according to Dalton's law of partial pressure. So our total pressure, P total, is going to be equal to 3.61 atmospheres plus 1.92 atmospheres, and that's going to be equal to 5.53 atmospheres. There's our answer.